Okay, it's 9 o'clock in Zurich, midnight in California, so it's a good time to start. So welcome everyone to the third day of Solstice of Foundations. And today we'll start with the second part of Leifer's talk on epistemic theories. So Nuria will be sharing the morning session. I will leave here in a little bit. So you can ask questions either directly on Zoom by joining the Zoom link that was shared on Discord, or on Discord, and then we relay them to Matt here. Okay, so Matt, whenever you'd like, you can start.
Thank you very much, Lydia, and welcome back. As I was saying at the end of last time, the first topic I'm going to talk about today is how we account for interference in these kind of theories. And then I want to give a bit of an account of the sort of more formal mathematical development of these theories. That's probably going to be a little bit rushed because there's a lot to say there. However, I have included in the slides at the end of the slides a long reading list. So reading list of what I think are the most important papers in this area. So you can, if you're interested in more of the mathematical details, you can look there. Okay, so yesterday I gave some quotes about the difficulty of understanding quantum interference. So what I want to do is start by breaking it down a bit more precisely. In the paper, we talk about what are called the trap phenomena. This is my main contribution to this paper, by the way, just coming up with this acronym. So TRAP stands for traditionally regarded as problematic. Okay, so the interference experiment we're going to look at is a Mach-Zehnder interferometer. Is kind of the simplest kind of interference experiment we can look at, and will allow us to deal with discrete degrees of freedom, unlike if we did the double slit experiment, we'd have to be dealing with the continuum. So this captures basically the main points of quantum interference in the simplest kind of experiment. So this is the setup we're going to consider. Remember, I said last time that you have to be very precise about which aspects of the phenomena you're going to reproduce, because with a Mach-Zehnder interferometer, you can pretty much do everything that you could do on a qubit, right? So if there are, if you said I have to reproduce every single possible experiment you could do on this kind of interferometer, then you'd have to reproduce all of qubit quantum mechanics, and we know that we can't do that with the toy theory. But what we want to reproduce are the things that have usually been argued are problematic, and that we can do. So we're going to have a Mach-Zehnder, a single photon in a Mach-Zehnder interferometer. We're only going to deal with 50-50 beam splitters. Here are the two beam splitters, and they are 50-50. We can put a phase shifter in one of the arms that we can set to either 0, so there's no phase shifter there, or a phase shift of pi. And we can also put a non-destructive detector on the path on one of the arms. It wouldn't be much harder to model a destructive detector that absorbs the photon, but it's just, for simplicity, I'm not doing that here. So this is just a non-destructive detector. The photon continues on after being detected there. So this is the setup. And so let's look at what are the usual phenomena. So suppose we insert a single photon on the left-hand path. So here, then what happens? If there's no detector present, no phase shifter either, then the photon will always be detected at the output on the path left. Okay, so the photon, the wave function splits up along these two paths, and then over here we get constructive interference on the left path and destructive interference on the right path, and so the photon is always detected here on the left path. So this is interference or wave-like behavior, if you like. On the other hand, if you put the detector in, then it will click with probability 1/2. Regardless of whether or not it clicks, the photon, there'll be a probability of 1/2 of the photon being detected on each path at the end. Okay, so just even this detector being here, the fact that there's a detection is made here, whether or not the photon is actually detected on this path or it's actually going on that path, it destroys the interference, and now we have a behavior more like a particle where it can come out on either of those two paths. Okay, so that's the basic phenomena that we're looking at. So what's usually regarded as problematic about this? Well, okay, so you can break it down into several things. Firstly, there's wave-particle duality, right? So the particle or the photon seems to be deciding whether to behave like a wave or a particle, depending on the type of experiment that's done. Okay, so how does the particle know whether the equipment is going to check a wave-like property or a particle-like property? This seems to induce an observer dependence of reality. Okay, because it's us that's choosing whether or not to put a detector in the right arm of the interferometer. Okay, and we could choose to put it in at the last minute. So it seems that the choice of the observer determines what kind of properties the system even has. Okay, so what is reality? There's an observer dependence. There's also the idea of that there's a failure to explain this in terms of local causes. The idea here being that since the detector, when you put the detector here, the particle changes its behavior. And that's true regardless of whether the particle is actually going on the left path or the right path, right? So if the photon goes down the left path, how does it know that there's a detector on the right path? There seems to be a kind of non-locality going on there. And then you just have this idea that superposition has to be a new category, because there's no way in terms of particles going down paths that you could explain why it always comes out on the left here. That we have to say that when the photon is in a superposition of being in left and right, something genuinely new kind of state of reality is present. The point here is that all of the phenomena we're talking about, however, arise in a suitable version of Speck's toy theory, in which none of these things are true. Okay, so we will always, we'll see how each of these things turns out not to be true in this model. Okay, so let me just go in a little bit more detail in the mathematical description of this experiment in quantum mechanics. So the usual way of describing this is, I'm going to discretize the system so that we can imagine that the photon is either traveling down this left mode or this right hand path. Okay, and I'm just going to denote the state where it's on the left hand path as L and on the right hand path as R. Okay, so we have this first beam splitter transformation here, and the beam splitter implements a unitary operation like this. The relative phase factor that you get here can change depending on the construction of the beam splitter, how the beam splitter is made, but basically it's something like this. So if there's no detector on the path, then all that happens is we put the photon in on the left-hand path at time t1. At time t2, it's gone through the beam splitter, so it gets mapped to this state. At time t3, we haven't put a detector here, so nothing's happened, still the same state. And at time t4, well, you can easily check that this unitary operation here is its own inverse. So if I apply this operation again to this state, it gets me back to L, and that's why you always detect the photon in the L, left path. Now, suppose we put a detector here, then up to time t2, everything's the same, but now we have the detector, and so with probability 1/2, the detector will click. If the detector clicks, then the state will collapse to being on the right path. If the detector doesn't click, then it collapses to being on the left path. Each of those happen with probability 1/2. So if we're in the left state, when we go through the second beam splitter, we end up in this superposition. If we're in the right state, we end up in this superposition. And both of those have 50-50 probability of detecting the photon on the left or the right path. So that's basically the phenomenon. We can also put a phase shifter in the right path. If there's a pi phase shifter in the right path, all that does is maps r to minus r. And so in that case, between T2 and T3, the state will go from being right minus left to basically right plus left, if you put the phase shifter in. And so then the final beam splitter will give you the right state rather than the left state. So if you put the phase shifter in, then the particle, it changes which of the two paths at the end get constructive or destructive interference, and you end up always coming out on the right path. So that's the basic phenomenology. However, it turns out that for us, it's going to be more convenient to redescribe this in, what's sometimes called the second quantized formalism, or in terms of Fock space, or in terms of modes, a mode description, a kind of field-theoretic description. Those are all names for the same thing. It's very important for the toy theory description of this that we're talking about a toy theory of modes rather than a toy theory of particles, right? So we need to understand how that looks in quantum mechanics. And if you've done any optics in quantum mechanics, then this will be very familiar. So now we're going to consider the left and right paths as spatial modes. Okay, so we're going to describe it in terms of like the left and right modes are now our systems. Okay, and you have a state which tells you how many photons are in that mode. Okay, so the Hilbert space is now a Hilbert space for the left mode and a Hilbert space for the right mode. So we're treating that as a composite system. We could, in this description, talk about multi-photon states. However, for the experiment that we're interested in, we're always in the one photon subspace. So the reasons why we're going to use this description are it's going to be more closely related to the structure of the toy theory. It also makes clear what's a local operation here, right? So, so when we do a phase shifter or a detection on the right hand, in the right-hand path, you'll see that it only acts on this component of the Hilbert space. Okay, so let's look at that in more detail. So now, when we put in a photon on the left mode, instead on the left path, instead of just calling that state L, we'll say that is one photon in the left mode, 0 photons in the right mode. And then our beam splitter now does this transformation, which in this description looks like it's an entangled state. So it's an entangled state of the two modes, even though this is just the same thing as right minus left in the old description. Okay, so again, with no detector, this state gets mapped to a superposition entangled state. Nothing happens between T2 and T3. And then we get mapped back, and this detector here responds to the photon that's in the left mode, and that clicks. No photon in the right mode, so this detector does not click. Okay, and then again with the detector in, again we're now going to basically just apply the detector on the right-hand mode here. So this projects. We do a projective measurement of basically 0 photons versus some photon. Could be more than one photon, but we're only dealing with one photon here on the right mode. And just by measuring the right mode, that's going to collapse the whole state either to this or to this. So you see that we only applying the projector on the right-hand mode here. It's clear that that's sort of a local thing in quantum mechanics. It's acting on the right-hand Hilbert space, but it collapses the whole state. Okay, and then we end up in a state where both detectors can collect with 50-50 probability. If we put a phase shifter in the right path, then if there's no photon in the right path, it does nothing. if there's a photon in the right path, it gives it a phase of -1, and that again changes the relative phase between these two components, and then the final beam split is going to cause things to come out on the right. Okay. All right, so now let's look at the toy theory. So usually, if you look at most of the papers on toy theory, usually we think of the toy bits as being analogs of qubits or particles, or the spin of a particle or something like that. So all you really need to do to capture these interference phenomena is to apply the toy theory to the field modes. Okay, so our toy bit, we're going to have one toy bit for the left mode and one toy bit for the right mode. Suggestively, we're going to give names. In this case, we're going to give names to the. So each toy bit has two binary variables. Remember, so it takes 2 bits to specify the ontic state of a toy bit. But we're going to give them names. One of them is we're going to call n, which is an occupation number. This basically tells us whether there's a particle there or not. It's a particle-like property. And we're also going to give the other variable the name phase. Okay, it is not the phase that appears in the wave function. It's not the same thing as that, but it's an ontic variable. But it is the variable that's responsible for the wave-like properties, if you like. Okay, so a single mode will be described by 4 possible ontic states, a specification of the occupation number and the phase. And note that even if there's no particle, there is still the possibility of having 2 different values of this phase variable. Okay, so when, as in the Mach-Zehnder interferometer, we have 2 modes, the left mode and the right mode, we will have now 4 possible ontic states for each and 16 ontic states for the system as a whole. Okay, so here's what the epistemic states are going to look like. And this is the sort of quantum states corresponding to them. So if I have no photon in the mode, then I know that the occupation number is 0, so I must be completely uncertain about the phase. So it's a situation in which there's no photon, but this ontic phase variable is completely uncertain. Similarly, in the case where I know that there's definitely a particle in the mode, I must be completely uncertain about the phase. Now, if I'm in the state 0 plus 1, this is a superposition of there being no photon and being 1 photon. In the toy theory, this is going to be represented by well, a situation where I am completely uncertain about whether there's a particle in the mode, but I know the phase, right? The phase is 0, is going to be 0, which corresponds to this plus here. And if I'm in the minus state, then it has to be the opposite conclusion. The phase is 1, but again, the particle occupation number is completely unknown. Now, so the important thing here to recognize is that the vacuum state, so this is the vacuum state. This is the state where there's nothing. There's nothing in the mode. So in the old description where we were describing it as, where we had a Hilbert space with the states left and right, this doesn't even have a state in that description. But in the mode description, we have, for both the left and the right mode, a vacuum state. And the vacuum state is an epistemic state, and it's spread out over 2 possible ontic states. Now, if you try to make the arguments for these traditionally regarded as, okay, so I have a question in the chat from Michael Theodorou, who says, what is phi exactly? So phi is just some ontic variable. So it's just some property that the 2 modes have. So we have these 2 paths, and on each of these paths, there are some properties. One of the properties is there a particle there or not? and the other property is phi, right? What is this phase value, right? So it's just some property that's going to propagate along these paths. What is it exactly? Well, it's just an ontic variable, a property, just like a, in the particle theory, you'd have a position or a momentum of a particle, right? So in this theory, we have an occupation number and this phase. Okay, it just is what it is, and it will be used to reproduce the phenomena that we have. Okay, so moving on, yeah. So an implicit assumption in making quantum interference look problematic is that sort of implicitly everybody who argues for this is thinking that if there is no photon in the mode, then there is nothing in that mode. Okay, this is kind of how you have to make the argument, because if you want to argue, for example, that there's some kind of non-locality, then you have to say, well, if the photon goes down the left mode but the detector's in the right mode, then how does it know that there was a detector there? Well, but if when there's no photon in the mode, there is still something propagating, there's still this phase value, then that can be the thing that tells you whether there was a detector there or not, right? So that gets rid of the need for non-locality. So if you look at the arguments for these problematic ideas, then they all sort of rely on the fact that if there's no photon going down a path, then there is nothing. There's literally nothing. Right, okay. So, however, in our model, the vacuum is represented by an epistemic state in which the occupation number is 0, but this phase variable can be either 0 or 1, and that can convey information to the second beam splitter. So, if we're going to make a model that's psi-epistemic, in which the quantum state is epistemic, it's not only natural, but actually necessary for the vacuum to be represented by a probability distribution with support on more than one ontic state. So for one thing, the vacuum state, the state 0, is a quantum state like any other. So if quantum states are like probability distributions and they're spread out over many ontic states, that has to be true for the vacuum state as well as anything else. Let's give a more rigorous argument for that. Okay, so let's consider that we can have the state 0, the vacuum state. We can also have these superposition states, these two superposition states, plus and minus, in which there's a superposition of there being 0 and 1 photon. So in whatever toy theory we come up with, there's going to be 3 probability distributions that get prepared when each of these 3 states are prepared. So mu0, mu plus, and mu minus, those are the 3 probability distributions. These 2 states are orthogonal, okay? So there can't be any ontic states which are in common in the support of both of these, because there's a measurement I can do that will tell me whether it's plus or minus. So if there was a common ontic state, then how would the measurement be able to tell which of those was the case? So there can't be any overlap between these two probability distributions. However, 0 and plus are non-orthogonal, and in a psi-epistemic model, the reason why states are supposed to be indistinguishable is because there's overlap in their supports. So that means that in a psi-epistemic model, there should be ontic states that are in the joint overlap of the vacuum state and the plus state. But the same thing is true of 0 and minus. Those are non-orthogonal. So there should be states that are in the joint support of both of these. However, we've already argued that there are no states in the joint support of mu plus and mu minus. So that means that there has to be at least 2 ontic states in the support of mu0, because it has to share one with mu plus and one with mu minus. So there must, in a psi-epistemic theory, be more than one ontic state in the support of the vacuum. Okay, so measurements, we can basically, well, all that's really going to be relevant to us, the only thing that we're ever going to do in this is do a measurement of the occupation number. Is there a photon there or not? Okay, so this is the measurement that we're going to be interested in doing. It just determines whether the value of n is 0 or 1. The state update rule will be as we've determined before. So you'll either determine that it's one of these two ontic states or one of those two ontic states. In the toy theory, in order to preserve the knowledge balance principle, that has to cause a disturbance. So with probability 1/2, nothing happens. And with probability 1/2, the phase just gets randomized. Okay, so measuring the occupation number randomizes the phase. Similarly, if you were to measure the phase, if you were to do a phase measurement, the occupation number would get randomized. So a question on YouTube: can the notion of decoherence be treated as a trap phenomena? People don't normally talk about decoherence. Okay, and then it continues. Are there some conditions phenomena should satisfy in order to be seen as trap phenomena? Well, okay, so the set of phenomena that I've outlined, this specific set of predictions of the Mach-Zehnder interferometer with either a detector or possibly a phase shifter in there, that's supposed to be the extent of the trap phenomena. That's all you need in order to make these arguments that people have made that there's something strange going on with quantum interference. Okay, so that specific thing is what we're calling the trap phenomena, to be clear. Okay, so then we have also the two-mode epistemic states. We're going to need these. So this would be, for instance, the state in which you put one photon in the left port of the interferometer and 0 photons in the right port. So that would be a product state distribution like this. And after the beam splitter, you're going to end up in a correlated situation where you don't actually know the value of either of the occupation numbers or either of the phases, but you do know their relationship. You know that they add to 1. Okay. So the update rule, if I measure the occupation number, then of one of the modes, of the right-hand mode, say, then I will distinguish this set of ontic states from that set of ontic states. It's a local measurement, so the phase of that mode will get randomized, but it happens locally. You see, nothing is happening to this mode, only between the two left and right things here. Okay, so the beam splitter transformation, this has to be represented by a permutation. It's a reversible dynamics. And it turns out that this permutation will do the job. Here it is mathematically. I have to specify the occupation number and the phase on the output for both modes. And this is addition modulo 2 here, these symbols mean. Okay, so it turns out that the occupation number at the output of the left mode only depends on the phases. And the phases of the left mode on the output depends on both the occupation number initially and also the phase of the right mode. Okay, so this transfers, what it's doing is it's transferring some of the phase information that's in the phases into the occupation numbers and vice versa. Okay, but it's sort of much easier to see what's going on if you look at these arrows here. So this is what happens in our theory. So in our theory, you start off in this product state, in this toy theory product state, then the beam splitter transformation happens. By the way, the beam splitters only happen when the two modes are next to each other. So the beam splitter is an interaction. It's the only part where the two modes interact. So if you look at what happens here, this square stays where it is, so that stays there. This one is going to go down. Well, actually, let's look at so this one's going to go down over here. This one here, that one stays where it is, and this one goes down to the bottom here. So you end up in this correlated state, which is the toy theory analog of this entangled state. If you have no detector between T2 and T3, then nothing happens between those two. Nothing happens in the toy theory otherwise. You do this beam splitter. It's very easy to see that this beam splitter is its own inverse because the permutation only swaps pairs of ontic states. Doesn't do anything more complicated than that. So if I swap a pair and then I swap it again, I get back to where I started. So the photon will always be on the left path. Occupation number will be 1 for that, and it will always be detected on the left path. If you have a detector, then the measurement, if I measure the occupation number of the right mode, then I'll either find it to be 0, which is this set of ontic states, or 1, which is this set of ontic states. So let's just look at what happens when it's 0. What happens when it's 0 is that, well, initially, I knew that the photon was in, well, sorry, that my 2 toy bits are in one of these 4 ontic states. When I find out that the occupation number of the right mode is 0, it means that I know that it's one of those 2 states. But then, with 50% probability, either nothing happens or I get the randomization between these 2 and between these 2. So I end up back in this state. Okay, so that's epistemic state. That epistemic state then goes through the beam splitter again, which is exactly the same as what happened in the first time we applied the beam splitter. We were in this state, apply the beam splitter again, we end up in this state, which now has a 50-50 probability of being, of detecting of the occupation number of the left mode being 1 and the right mode being 0, or the right mode being 1 and the left mode being 0. Okay, so a similar thing would happen if we'd have detected, if we'd have not detected the photon in the right mode, if we'd have detected the photon in the right mode. So this is what happens. This is what happens when you don't detect the photon in the right mode. If instead I was here, I would end up in the epistemic state that's these 4. It would do a similar thing. It would go to a different correlated state, but it would still have a 50-50 probability of the left or the right mode being occupied. If we put in a phase shifter on the right mode is just represented by this permutation. And so if I look at what its effect on the joint system is, it's going to be this. So the right mode is always the one along the bottom here. And you can see that what that would do, if we, after the beam splitter were in this state, what that would do is it would just put you in this correlated state instead, which is the analog of this entangled state down here. And then if you didn't have a detector and we applied the beam splitter, that now puts you down in this state where the occupation number is 1 for the right mode and 0 for the left mode. Okay, so you can extend this model and do other things, which we talk about in the paper. You can do, if you know what these things are, the Elitzer-Weidman bomb test experiment, the Wheeler's delayed choice experiment. You can extend the model. You need to introduce another toy bit, but we can do the delayed choice quantum eraser, and some versions of counterfactual computation and communication can be done in this model. So many other interference phenomena which I claim to be non-classical can be reproduced in this way. And the important thing to note here is that in our model, the photon always either goes down one path or the other. Like the occupation number of either left or right is always 1, and the other one is 0 at all points during the experiment. It's local. The photon never sort of jumps from one path to the other. The only thing that local manipulations happen, local measurements of the occupation number, local shifts of the phase happen, but there's only interactions between the two systems when we're at the beam splitter. So it's completely local model. Okay, so wow, I've used most of my time. 10 more minutes to go. So I want to move on to the second topic. I won't get through much of this, but I just want to give you a flavor of how you can build the general mathematical formalism of this. So, Rob Speckens introduced this terminology, quasi-quantization. So there's a way, quantization, canonical quantization is a way of taking a classical theory and coming up with a quantum theory. Quasi-quantization is a way of taking classical theory, imposing an epistemic restriction on it, and getting to a toy theory. So the reason we need this is because the knowledge balance principle is not applicable to all systems. So for instance, if you had a system which requires 3 binary questions to specify the ontic state, so that would be something with 2 to the power 3, 8, 8 ontic states, then there's no way I can know half of those, right? I have to know 1 or 2. Or even if you have a system with a continuum of states, then what does it mean to know half of the bits of information about it? Well, there's an infinite number that is needed. It's also, even to systems which it does apply to, it's difficult to apply and makes the relationship to classical mechanics and to quantum theory of these theories more obscure than it need be. Okay, so let's look at this quasi-quantization briefly. So what you do is you start by considering Hamiltonian mechanics. It really is classical mechanics, ordinary classical mechanics in the Hamiltonian formalism on phase space. Okay, then quasi-quantization imposes an epistemic restriction. So the guiding analogy here is that in quantum theory, a set of observables is jointly measurable if and only if the observables pairwise commute according to the commutator, the matrix commutator. In our epistricted theory, well, there's always a definite state of reality, but what we want to do is impose an epistemic restriction on what's jointly knowable. So what we'll do is in Hamiltonian mechanics, we have the Poisson bracket. It's the classical sort of, the commutator is supposed to be the quantum replacement for the classical Poisson bracket. So if we have variables that pairwise commute according to the Poisson bracket, then they are jointly knowable. You can know their values at the same time. We're also going to, and this is something that personally I don't like very much, but it's done because it gets us a theory, restrict attention to quadrature variables. So these are just linear combinations of the fundamental phase space variables. So if you're in an ordinary continuous phase space with a position and a momentum, it would just be a linear combination of position and momentum would be your quadrature variables. Okay, so then the epistemic restriction, Speckens calls it classical complementarity. It's kind of, in some sense, a quantum, and toy theory analog of complementarity. So the valid epistemic states in the theory are those wherein you know the values of a set of quadrature variables that Poisson commute, and of everything else, anything that's sort of canonically conjugate to those variables, you are maximally ignorant of. Okay, so this is fairly straightforward classical mechanics. If we deal with continuous degrees of freedom, we can construct this theory fairly easily. The difficult part is going to be doing it for discrete degrees of freedom, like the toy bit theory that we've been talking about. So if you have n degrees of freedom, say, which could be the positions in one dimension of n different particles, or they could be, the first 3 of these could be the position in 3D space of the first particle, but we just have sort of n position-like degrees of freedom. Our configuration space is Rn, which is just you specify n positions. The phase space will give you a position and a momentum for each of those degrees of freedom. So we can specify that by a vector in R to the 2n. We'll call our phase space omega, and these vectors labeled m in that space. Now, the physical quantities, the variables, such as the energy, for instance, are functionals on this phase space. They are functions that take one of these phase space vectors to a real number. Okay, and then the Poisson bracket is defined in this way on phase space. So you evaluate these functionals you take in terms of the derivatives. The quadrature variables are just linear combinations of these fundamental variables, where these coefficients just take numbers, are just real numbers. Now, if we have a quadrature variable as opposed to a general functional, we can associate the vector with also the functional with a vector in R to the 2n. You just take the coefficients and you list them in a vector. And so these quadrature vectors are particularly nice because for them, the Poisson bracket, you can work this out, the Poisson bracket just turns out to be this thing, which is called the symplectic inner product. So it's a kind of inner product. So you have these two vectors, but there's a matrix in the middle. And this matrix in the middle is this J, this symplectic matrix J. Okay, so that's how you calculate this inner product. You take your vector representing the functional G, multiply it by this matrix, and then you take the inner product with the vector F. And this calculates the Poisson bracket for quadrature variables. Okay, so what do you have to do? So I'm really running out of time, so I'm going to have to go through this really quickly. If you want to have discrete degrees of freedom, then the way you basically do it is you replace the real numbers here by a finite field. Okay, so a finite field, and then you do everything the same. Now, finite fields can be kind of complicated in general, but if we are doing so the order of a finite field is the number of elements it has. If our order is a prime number, then the only finite field in that case is addition modulo d. Okay, so ZD. So that just means we take these discrete set of numbers, and addition is just sort of modular arithmetic, clock arithmetic. Okay, so when you get to D, you reset back to 0. Okay, so you do basically everything that I did before, except with these finite field variables. Okay, so configuration space is just these position-like variables. Now I only take these finite set of values. Phase space, the similar thing with the momentum values as well. The functionals now have to map you from this phase space to this discrete set of numbers. And now, since we're in a discrete space, the Poisson bracket can't be defined in terms of derivatives. There aren't derivatives on this discrete space. So what we do is we replace the derivatives by finite differences. So what this just means here is that, I add 1 to the position, to the jth position variable, and I don't do anything to the momentum variable here. And here I'm adding 1 to the momentum variable and not to the position variable. So this is sort of just like the derivatives that we had here, except just we're dealing with finite differences. And then the quadrature variables are, again, the coefficients now have to be in this discrete set of values. And we can again associate this with a vector, which is now a vector where the elements are in this finite field. And again, you determine that this Poisson bracket is a symplectic inner product. So it's the same structure as we had before with this symplectic matrix. Okay, I've kind of run out of time, but what you do is you impose the epistemic restriction, this classical complementarity on these theories. And if I impose it on this case, I get something which Beckens calls quadrature. The epistemic it's a continuum quadrature epistemic theory where you can have you can have states where the momentum is known, but the position is completely unknown, and vice versa. But for two particles, you can also have analogs of the EPR type of state, where you know the relationship between the positions and the momenta, but nothing else. Okay, I'm being told I can take 5 more minutes, so I will. Okay, in the discrete case, if this number d is 2, then I will get precisely the Speckens toy bit theory that I have described earlier. But for larger values of d, you'll get other things. So you can have a toy trit with d equals 3, for instance. And I should say that all this has been generalized to arbitrary finite fields. I'm just not doing it here. It was done in a paper by Catani and Brown, which you can find in the reading list if you want to see that. Okay, so yeah. Okay, so here's just an example here. So I don't know where, x should be q here, sorry, I'm sorry. So here's an example of variables that commute. If I take 2 position variables, then you can know the values of q1 and q2, but then the momentum variables, because they're canonically conjugate, because they satisfy this, their Poisson bracket is equal to 1. That tells you, classical complementarity tells you that in that case, the p values would have to be completely uncertain, right? Okay, similarly, but you could also, for 2 particles, you could know the sum of the 2 momenta. And then you could also know the difference between the 2 positions, but you would have to be completely uncertain about the sum of the 2 positions, which would mean that you're completely uncertain about the 2 positions themselves. I'm not going to go through this, but there's a whole mathematical formalism that you can develop for how to write down the valid epistemic states. More interestingly, the dynamics now becomes easy to do, because before you had to check, when you have a composite system, you had to check that the permutation that you were doing satisfies the knowledge balance principle for the individual systems as well as jointly. But now we can just impose that basically the reversible transformations are those that preserve the Poisson bracket. Now, in a continuum theory, those would be the transformations that are generated by a Hamiltonian. In a discrete theory, we don't have a continuous evolution, we only have discrete evolution, but we can have the analogous thing. So it's called the group of symplectic affine transformations, or the Clifford group, and they are just symplectic transformations. So those are matrix transformations that preserve the symplectic in a product. And you can also do a translation in phase space. You can add this component. And in the discrete theory, this would be addition modulo d. Okay, so you can have things like a rotation in phase space or a translation. Okay, so those are much easier to find and much easier to check that condition than it is to go through the whole knowledge balance principle rigmarole. And then the repeatable measurements that you can do are any commuting set of quadrature variables. You can measure those simultaneously without upsetting the epistemic restriction. Okay, so we can reproduce the toy bit theory and construct for any prime d. Has been generalized to all finite fields. The continuous variable theory you get is an interesting one, but there's another continuous variable toy theory which was proposed, which is called the Gaussian theory, and it's different from that. So there's a little bit of a disconnect that goes on there. The relationship to quantum mechanics here. So these are theorems that are proved in the prime case by Speckens in his paper and have been proved in the more general case by Catani and Brown. So if you have odd value of d, the toy theory for the finite fields of order d is the same predictions as stabilizer quantum mechanics on a d-dimensional Hilbert space. So it gives you the stabilizer subtheory. Continuous variable theory is equivalent to quadrature quantum mechanics, where the states are joint eigenstates of commuting sets of quadrature operators, and the transformations are the one that preserve those set. So you get things like the EPR state appearing in that theory. What's kind of remarkable about this is that all of these are underlying this is classical Hamiltonian mechanics. It's just classical Hamiltonian mechanics. Okay, the discrete version in some cases, but that's all it is. It's a really literally classical theory of classical physics. And the only thing we've added is this epistemic restriction. And by doing so, we've ended up at something that is operationally equivalent in terms of its predictions to a subtheory of quantum theory. So it's just classical mechanics, but it's equivalent to a subtheory of quantum theory. Okay, so to conclude, many puzzling quantum phenomena exist in a theory that's literally classical mechanics, but just with an epistemic restriction. They operationally reproduce some subtheories of quantum theory. The toy bit case, sorry, is anomalous. I should have said that. It's the odd dimension is important there. Anything that appears in these theories can't really be the source of quantum computational advantage. That's one of the reasons why it's interesting to look at these. Here are the things that are not in the toy theory. So you can't have a Bell inequality violation, you don't have any contextuality, and you can't prove the reality of the wave function in these theories. So therefore, those are the things that are really interesting to look at according to this. Since I'm over time, I'm going to just leave it here. There's lots of open questions about the toy theory, right? We don't really have a proper toy version of field theory. I think the restriction to quadrature variables is a little bit artificial, and you might get some interesting things if you, for instance, considered things like the modular momentum, which Yakir Aronhoff is fond of. Okay, so I'm going to leave it there. Thank you for your attention. I can, if you like, respond to some of the questions that have appeared in the chat, or take other questions from the room. Shall I start with the chat?
Yeah, thank you, Matt, for the talk. Yes, there's many questions on the chat. Maybe I can start with the easy one. So someone asked why we need D to be a prime number.
Okay, so we don't need D to be a prime number. What we need is to so the values that we're talking about, they have to form a finite field. Okay, so we need a finite field, and it's just the case that when D is a prime number, the only finite field in that case is addition modulo D. When you have a non-prime D, the structure of the finite fields is more complicated. So I'd have to go into a more complicated discussion of how those work. But you basically just do the same kind of thing with a finite field as I was doing with integers modulo D. And if you want to see that construction, look in the Catani-Brown paper in the reading list, or indeed Lydia and Nuria's review article that discusses that.
Mm-hmm. Yeah. And someone else is asking whether you can reproduce the Hardy paradox.
Yeah. So it's interesting. You can't reproduce the Hardy paradox, of course, because the Hardy paradox is a proof of non-locality. What we're doing here is single photon experiments. However, there was an earlier paper by Hardy, which is kind of very similar to the Hardy paradox, in which he used it to try and prove the reality of empty waves in Bohm. Well, not in Bohm theory, but the reality of empty waves. So, if the wave function is somewhere, but the particle isn't there, in, say, a theory like Bohm mechanics, he was trying to come up with an argument that those empty waves are real. you can reproduce that experiment using the toy theory. But the Hardy paradox is sort of a modification of that because the measurement bases it involves don't exist in the toy theory, and it can't be reproduced. It's not really because it involves two photons, because the two photons never really end up in the same mode, but it's because of the measurement bases that you need in that paradox.
Thank you. And there was this question about whether it's about this decoherence, if it's related to this trap phenomena.
Yeah, I'm not quite sure what that means. I mean, so I mean, you can certainly, like, if you want to talk about the trap phenomena, if you want to talk about sort of the church of the larger Hilbert space, or the sort of many worlds approach to things where you never collapse the wave function, you can certainly, instead of the detection measurements, say, okay, the system is interacting with a detector in a unitary way. And you can certainly model that in the toy theory by a permutation with another system. In fact, when we're doing the quantum eraser experiment in our paper, that's the way we have to do it. And you certainly see that would also reproduce the statistics. It acts like a detector in the sense of randomizing which detector fires. So you can certainly, if what you mean is, can I model my measurements as interactions, physical interactions, and then possible interactions with more things in the environment, yes, you can certainly do that here and still reproduce everything.
Okay, very good. So there's a few more questions going on Discord, but I think maybe we'll let people go for the coffee break now, and
Sure.
you can answer them tomorrow or evening. So thank you so much for joining us. Yeah.
Yeah. Okay. No, thank you. I'm sure, as last time, you and David will have a go at it overnight, and then I'll wake up and have no questions to answer. That will be fantastic. But, thanks everybody.
Yeah. By the way, if you have any open positions that you'd like to advertise at the moment, or internships or anything, not right now.
Unfortunately, we don't at the moment, but
okay. I'm sure people will be happy to hear about this in the future. Okay, so very good. So we restart at 10:30, so you can have half an hour coffee break. Thank you so much, Matt, for joining us, and good night.
Thanks.